Okay, welcome to the final session. Everyone can sit away.
Thank you. Yeah, so I'll be talking about higher order DisCoCat and what we call the Peirce-Lambed-Montague semantics. So this is joint work with Giovanni de Felice, and it's basically a summary of the 500 pages of our two theses combined in half an hour. So let's get started. So the outline is made of these 4 characters. So I guess Bob was one of the founders of this DisCoCat model, which we can define as a functor from some grammar G into finite dimensional vector spaces. So I'll explain that quickly. And then I'll give it a bit of background on these Lambek grammars and define them in terms of categories. And then I'll explain how you can formalize Montague semantics as a functor, which goes from grammar now into a free Cartesian closed category, which I called lambda L, where now you interpret natural language in terms of, not in terms of vectors, but in terms of logical formulae. Then we'll go through the ideas of Peircean logic, where first all the logic formulae are represented as diagrams. And finally, we'll wrap all of this together and we'll get this definition of higher order DisCoCat models, where instead of logic, we've got diagrams. So what is DisCoCat? So maybe you've seen this picture before. We've got a noun on the left for the subject, and it's going to be represented as a vector of dimension n. We've got a noun on the right, and in the middle, we've got this tensor is, which has 2 inputs and 1 output. And so this is a tensor of order 3. And so the DisCoCat model, you can summarize as this functor from grammar to vector spaces. First, you take your sentence, parse it as a morphism in a closed, actually here in a rigid monoidal category. So this is something you can do automatically. You can train a parser to take strings of words and tell which words have which types and how do you connect them together. Then once you have grammatical type T, you got to send it to some finite dimensional vector space. So for example, the nouns will go to some fixed dimension n, and then the verb is will have to take n-dimensional vector, 2 of them, spit out an s-dimensional vector. And now to compute the meaning of a sentence, we just apply the functor from our pre-group grammar, so this rigid category G, into vector spaces. And that amounts to taking our diagram and contracting the tensor network. So the cups of the grammar, which tell which word is connected to which, turn into tensor contraction. So that's a brief summary of this DisCoCat model. And what is it good at? So I guess the reason it was introduced, where the name comes from, so cat is for categorical, but the co comes from compositional. So we want this symbolic approach where we have this parser that explains how the model computes. You can visualize it, you can reason about these. And it's also statistical in the sense that inside of each of these boxes, you have vectors that you can learn from data. So you can use, well, essentially machine learning, but with this symbolic approach to glue machine learning models together. So it's also got this really nice graphical language to reason about information flow in sentences. And what became the topic of my PhD thesis was that you can take these diagrams for sentences, and there's a very natural way of implementing these on quantum computers. So we use that fact to implement quantum natural language processing. And yeah, I guess there the idea was that these cups will correspond to entangled states in quantum mechanics, and you have this famous zigzag equation, cups and caps cancel to do an identity, and this is something you can use to give a meaning to these grammatical sentences in terms of quantum circuits, and use quantum computers to do NLP. And I guess I need to motivate this talk. So why is DisCoCat not enough? What are the cons of it? So the first one would be that it's really hard to train on big data sets. So you've got these sentences that have, each sentence has different shape. You can't really batch sentences together to speed things up with GPUs the way you would do in large language models like ChatGPT. And you've got this curse of dimensionality. So if your nouns have 1,000 dimensions, which would be a typical number for some large language model, then in this case, you would need adverbs to have 1,000 billion dimensions. So for each leg of the tensor, you multiply the dimensions. So you get words that are represented by absurdly large vectors. And I guess another limitation is that it's all linear maps. So essentially, the words are vectors, the grammar is a linear map, and there's no way of encoding things like negation, element-wise negation of the entries in your vector, because there's no linear map implementing it. So I guess to give some context on explaining how these grammars work and how you formalize them in terms of categories, it all starts in the 30s. So there's this first paper from Ajdukovic where essentially he's got this intuition that we can understand syntax of natural language in terms of this very simple equation that you've seen in middle school, where you take a number x, you multiply it by a fraction y over x, you get a y out. And the idea is that x is going to be the noun, the subject of your sentence. Y over x is going to represent a verb, which takes x as an input and gives y as an output. So you replace the equality sign by an arrow in this way. And I guess now you take this fraction bar and you just tilt it to the left or to the right, and you distinguish between essentially fractions on the left or on the right-hand side. That was the introduced by Bar Hillel. And then Lambek came in and realized that you can essentially formalize all of these in terms of closed monoidal categories. So in the first two, they were essentially considering lists of these types and deductive systems on lists of types. Lambek introduced this tensor product operation, and then he made this connection with the work that he did on logic with Cartesian closed categories. And here, essentially, you just remove the Cartesian, you just have monoidal categories, and you get this, what is called a Lambek grammar. So the definition is simple. You've got a set of basic types, so sentence, noun. Noun phrase, for example, would be examples of atomic things. Then you've got vocabulary, all the words in your language, and a dictionary, which tells you for each word in the vocabulary, what are the possible types for it. So you've got this free algebra over slashes on the left, on the right, tensor product, and a unit. So all the terms that you can form with these slashes and tensors, and then for each word you assign a number of these types. So for example, the word type will have two types. It can be a noun, a type, or it can be a verb, I type. So these will be different dictionary entries. And then in practice, people also add a bunch of ad hoc rules. So just ways of turning one type into another. So that's a categorical grammar. So that's the data you need. And then from this data, you define the language of the categorical grammar as the set of strings that come with a morphism from that set of string, that set of words, that string of words, to the sentence type. And this morphism lives in a free monoidal closed category, where the generators are your words with your dictionary entries. So for each word, you have a type. And then the only morphisms that you have come from this currying. So if you have x tensor with y to z, you can flip the x input to the output with the equation on the left, this isomorphism on the left, or you can switch the y input to an output in this way. And so these are all the rules you need to model natural language with categories, in the sense that with this definition, you get context-free grammars. And so any language that can be described in terms of a bunch of dictionary entries, such that it's in the language when there exists a morphism of this shape that defines all the context-free grammar, all the context-free languages. So that was, yeah, in the 50s. I guess an example here would that be with a bunch of words. Female said an astronaut sets a new record. Then female would be an adjective. It takes a noun, gives a noun, but it takes a noun on the right-hand side, gives a noun on the left-hand side. And then new is an adjective as well. And sets takes a noun phrase on the right-hand side, gives a noun, takes a noun phrase on the left-hand side, and gives a sentence. So here the notation is a bit different, but yeah. So you use the rules at each step. Here you have a rule of your monoidal closed category. So here you've got n to n, you cancel it with an n. Here you've got an ad hoc rule, just a noun can also be a noun phrase. And finally, you get a sentence type at the bottom. So this sentence is grammatical. So now Montague semantics is the idea of we've got these morphisms in a categorical grammar where we've got this currying isomorphism underneath. And well, there's another place where we have this currying, it's in the lambda calculus. So we can also define the lambda calculus in terms of 3 Cartesian closed categories this time. And so the idea of Montague was that we can take the grammatical structure and turn it into the structure of a lambda term. We evaluate this lambda term, and in his case, we get a logical formula. So here for thetas, for example, mortal is a noun, so it goes to just a symbol of your logic. The determiners like do some higher order plumbing of nouns, and essentially what you get at the end once you apply these lambda terms together, it simplifies to a logical formulae on the top. So from the grammatical structure of your sentence, you get the logical formulae that interpret that sentence. And so, yeah, this idea of English as a formal language, of semantics, of natural language as a homomorphism from syntax to logic via the lambda calculus. So how do we formalize this in terms of categories? Well, we want a free Cartesian closed category where now the primitives are going to be operations of our logic. So we've got some constant symbols, some unary predicates, binary predicates, some nullary operators true and false, and a unary operator for not, some binary combinators for and or. And these come with 2 basic types, I guess I must say, with tau for the terms and phi for the formulae. So for example, a quantifier will be something that takes a predicate, so a function from terms to formulae, and returns a new formula. And now in this free Cartesian closed category, the morphisms that of type phi, so the closed terms, the closed lambda terms will reduce to first of the logic formulae. So yeah, that's a way of encoding first of the logic, the syntax of first of the logic as lambda terms, and so the syntax tree of your logical formula becomes the syntax tree is encoded as the syntax tree of a lambda term. And so L will be the signature, so the set of operations I have in my Cartesian closed category, and this big lambda L will be the free Cartesian closed category generated from it. So now I can take a functor from my grammar to lambda L, and this functor will send sentences to formulae. It sends noun phrases to predicates. So nouns will take a term and give you a formula. Like it takes man and it gives you the formula is a man, or it takes a variable x and it gives you the formula x is a man. And then I guess the magic happens in this interpretation of noun phrases, where you've got this continuation passing style happening, where essentially noun phrase will be something that takes a predicate and returns a new formula. And so this is where you get all the magic happening, because you can encode determiners, so something like every, which takes a noun and gives you a noun phrase. You can make some magic happen where this will introduce a quantifier, and this quantifier will have a variable that will be shared in the left and the right hand side of the formula. So there's some copying implicitly happening here, some magic. And I guess an example would be you start from Alice kills a mortal, you parse it, and then you've got at each node the type for the subtree, and here at each inside the node you've got the lambda term that corresponds to it. At the very end you get the formula for the sentence. Another example here introducing a conjunction. And yeah, so so now that we have this Montague semantics as a functor from grammar to essentially this Cartesian closed category of logical formulae, we want to replace logical formulae with diagrams, so that instead of having this for all there exists notation with variables, we keep track of the variables as string diagrams, as wires in a string diagram. And so that's what Peirce gives us. So it goes back all the way to 1882. So he came up with this syntax for first order logic without variables. So independently from Frege and this for all there exists notation. And he was using these diagrams, which were really hard to publish. And so it remained sort of some secret handwritten manuscripts until 1906. And here's how it starts. It's come on my reader, and let us construct a diagram to illustrate the general course of thought. I mean a system of diagrammatization by means of which any course of thought can be represented with exactitude. So I guess Peirce was essentially doing applied category theory 150 years before it was cool. And he got rediscovered recently and formalized in terms of these, essentially these Frobenius algebras that you recognize here. And these give you the axiom of the Cartesian bicategory, which were introduced to think about databases in the first place. But essentially, you can formalize Peirce in this context where you've got this operator that takes a morphism and wraps it into a negation. And then here are the axioms from Peirce. You can go even crazier, introduce colors. And so the parity of how many bubbles are you nesting becomes the alternation of black and white. You've got this beautiful presentation of all of first of the logic with these crazy diagrams. And yeah, so now we had these functors from grammar to first of the logic. We want to replace first of the logic with diagrams. So we need essentially a Cartesian closed category where the terms will be diagrams. And so we're going to take a signature for our diagrams. So we've got a bunch of wires, a bunch of boxes, the domain, the codomain. And now we're going to say that the objects of our Cartesian closed category are pairs of lists of types. So the objects are the interfaces of my string diagram, if you will. And now I'm going to have a symbol for each box of my signature, which is just a term of type x goes to y. The identity is a term of type x goes to x. The composition is x goes to y, then y goes to z, you get x goes to z. And the tensor here, you just do the concatenation of strings. And so now the lambda d that you get, this free Cartesian closed category, it will be such that the lambda terms, the closed lambda terms, reduce to string diagrams. So essentially here, a lambda term will be the syntax tree for a well-typed string diagram, which goes from x to y. So I guess if you have if you have open variables, then it will be a string diagram where some holes are missing for including diagrams, nesting diagrams inside. So you've got this lambda d, and now you just play the same game and take functors from a grammar to the free Cartesian closed category generated by the signature of string diagrams. And here's a very simple example. We're gonna send the nouns to just some box. So our noun car is just this little box here, which has one output. Then the adjectives will take boxes of this type and return new boxes. So something like post-composition by a box. So if I take big, it's a function that takes a state, a box x, and returns x followed by big. And now I can implement this toy model where the word very will just double the adjective. So very big just means big, big. And so it's a silly example, but it's an example of something you can't really do with a linear model, right? You can't copy vectors in the normal DisCoCat models. And in this case, well, you can do whatever you want. You've got the lambda calculus, this sort of meta language where you can copy variables. So you take the big, you apply it twice to your thing car, and you get a car which is big, but very big. So you can also recover the normal DisCoCat if you just interpret things in a kind of trivial way where Alice will go to just a noun Alice, and loves will go to something that takes a subject, an object, and return the pre-group diagram, so the DisCoCat diagram for Alice loves Bob. So essentially that amounts to taking a monoidal closed category and then collapsing it to these rigid monoidal categories. And so you recover the old stuff, you get new stuff because now you can apply these higher order operators, for example, applying a function twice. But you can also introduce more syntax. So one thing that we found very useful was to have in our diagrams boxes that could contain diagrams inside them. So that would be just adding a new symbol to our syntax where each box F now comes with a bunch of holes that you can plug diagrams into. So this box F has holes for a diagram from Z1 to W1 and so on. And it's just going to be a new symbol in our free Cartesian closed category. So now we have lambda terms where some of the expressions are these boxes with holes. And so here's an example. You can take the word with, an adverb, which takes two nouns, or a coordination, which takes two nouns, and fits them inside a box with a hole. So the concepts coming in on the right, attitude coming in on the left, concepts on the left, attitude on the right. And then essentially what you're doing is just rewriting a syntax tree which goes top to bottom into one which goes inside out. So it's nesting. So you get this sort of third dimension in which you can compose things. You can compose them in sequence, you can compose them in parallel, and you can compose them inside out with nesting of boxes. And yeah, I guess now we can get to logic by interpreting negation as one such box with a hole. So negation is this circle which takes a diagram inside and returns a negated diagram. So we've got the predicate for man, the predicate for hot, and then this negation operator will take the guy on the right-hand side, wrap him inside this unary operator, which negates hot, and then plug it with the guy on the left. And so you get this negation, man is not hot. So the way you read these diagrams is every wire corresponds to a variable. And so here you've got a variable x, you've got m of x, and not hot of x. So we get to the main definition in what we've worked, which essentially takes Montague semantics, replaces the logical formulae with diagrams. And the way this works is a sentence will go to a closed diagram, so no open wires. A noun will go to a diagram with one open wire for a noun space of some dimension n. And then the noun phrases is where all the magic happens, where essentially a noun phrase will be something like a post-composition. So a noun phrase is something that takes a variable, a diagram from n to x, and it plugs something in there to get 1 to x. So for example, Alice is a noun phrase, and it will correspond to take some states and plug Alice in there. So here's an example. Alice takes an f and returns Alice followed by f. Now, same for mortal is just a noun, so this one will just correspond to a single box, and the determiner will turn it into a noun phrase. And now you've got this binary relation here, kills, which takes two predicates, composes them, and applies them to this, this binary predicate kills. So you apply kills to a mortal, you get this guy, which takes the guy on the left and plugs the whole thing together. And so you've done the same thing as Montague semantics, but now instead of conjunction, you've got tensor product of diagrams. Instead of variables, you've got wires in a string diagram. And essentially the composition of your diagram will give you relational composition. So there exists an x, there exists a y, such that a of x, m of y, and k of xy. So here's an example with a conjunction. So the adjective big will just take a noun and it will do the conjunction of it with big. So this is a variable x, which is true. So b of x is true and f of x is true. So this adjective takes an x and returns this guy. And now you plug the whole thing together. And this every, I guess, is where the magic happens, is you take two, you take a noun and a noun phrase, and you return this nested bubble, which means that not f and not g. So the implication of f implies g. Plug the whole thing together, and you get not there exists an x, such that b of x, m of x, and not s of x. So every big man sleeps. Right. So final example. I guess a very simple one. You've got this negation operator no, which takes some state and returns. So this guy will take a state and a predicate, and it will return the state followed by the predicate, the whole thing negated. The is will just take two predicates, apply them to the identity, and ta-da, you get there exists, so not there exists an x such that m of x and I of x. So yeah, I guess that's the general recipe. You've got these three categories. The one on the outside, the white category, if you want, is the category of grammatical structures. The green categories is where the lambda calculus happens. So you can have these higher order functions. You can have copying. You can do anything as any lambda term. And then this red category is what you get once you reduce this lambda term. You get a string diagram. And yeah, I guess I get some time to just show that the implementation fits on the slides in a sense that you can just import DiscoPy, create a small class for your formulae with the evaluation as a functor into tensors. Then you've got the bubble, which is interpreted as element-wise negation. You construct your diagram for the sentence. So no man is an island. This is what parsing looks like. And you construct this big functor. So this is the table from the previous slide. It's written in Python. Alice goes to lambda f, returns a goes to f. And now you generate some random bits to evaluate the model. And what does it mean to evaluate it? Well, you take the sentence, apply the functor, evaluate the results. So you get now a diagram, and you evaluate this diagram in your model. And now you can check that evaluating no man is an island gives the same as all not is man or not is island for X in your universe. And yeah, I guess that concludes the talk. I'll leave with a meme for the end, and I'll take some questions. Thanks. You can ask a question about Wittgenstein or something, some language games. Go ahead. Yeah. Mm-hmm. Yeah, I mean, can you wait? What's the second part of the question? Yeah, I mean, I guess there is some ideas behind this that like these diagrams are closer to the way humans reason than the lambda x for y notation that sort of traditional logic uses. And there are already tools that can take any arbitrary piece of text, and especially simple English, and pass it into these categorical grammars diagrams. And so it is possible in theory to just run through all of Wikipedia simple English and translate every sentence as a diagram. Then I guess the question is, what do you do with these diagrams once you get them? And you run into a lot of problems of training these models is really hard if you want to actually interpret them in terms of matrices or neural networks and so on. But yeah, in practice, you just need to give an interpretation to each type of word. So you know how to treat binary verbs and ternary verbs and adverbs, and you make the list of all grammatical types, and you can implement, you can turn any of Wikipedia sentences into diagrams.
Magic gathering is Turing complete. And it's also an example of a constrained natural language.
Constrained, yeah, I guess if it's Turing complete, it's not so constrained, right? But...
Right. Well, Turing complete in a very abstract way.
Mm-hmm.
Funny video on YouTube. It's a constrained natural language in which the card effects describe the effects of the game.
Mm-hmm.
So, like, could you model that system in this, and then could you diagrammatically show game states?
Yeah, I mean, so I guess there's no limit to this in a sense that if you can draw the string diagrams and you can interpret natural language in terms of string diagrams, then anything is possible, really. But I guess the point is the string diagrams themselves. This is efficient. You can produce diagrams for a sentence in polynomial time. Then all of the lambda calculus stuff inside is simply typed, so it's also guaranteed to terminate, no Turing completeness there. But I guess inside of the diagram themselves, you can interpret those diagrams as arbitrary functions if you want. So the rules of magic, if you feel like it, yeah. Yeah.
Right. I think.
Yeah, I guess the one answer very quick would be that you get diagrams that are much smaller because, for example, adverbs do not need to introduce these huge tensors anymore. You can represent them explicitly. And also, you do not need to implement things in terms of tensor anymore. So you could implement these as probabilistic processes if you want. There's no, you just need a monoidal category and you can interpret any sentence. So you're sort of away from the limits of everything needing to be linear.
Okay, so thanks, Alexis. Again.
Thank you.